Chapter 2, Section 1, Quadratic Functions and Models. In Chapter 2, we're moving out of that linear stage and into polynomial and rational functions. So polynomials, we're looking at x raised to the power of n. That could be x to the second, x to the third, x to the fourth. We're also looking at rational functions, so 1 over x to the power of n. We're going to start kind of at the beginning of the polynomial functions, one up from linear, looking at quadratics. So again, a polynomial function, you have a coefficient, you have your variable. Your next coefficient, your variable, your next coefficient, your variable, all the way down, the last term you see would be a constant value. So in this section, we're looking specifically at second degree polynomial functions, which you're going to commonly hear, those are quadratics. And you should have gotten some exposure to these in Algebra 1, a whole lot in Algebra 2. So what we're looking at you should be familiar with, but we're going to be going into a little more detail for some of it. So the definition of a quadratic function, we have f of x, we have ax squared plus bx plus 3. So the most you should see is those three terms. Your term to the second power, your term to the first, and then this plus c, which is your constant. If you think back to transformations of functions, the plus c at the very end, it's after the squaring, it's after the first term. So what we're looking at, that constant c, is a vertical shift. Okay, and this also has some other properties as well. So two of the big things that we're going to look at with these quadratics are the axis of symmetry and the vertex. Those are two really defining characters of these quadratic functions. So the axis of symmetry, let's get a coordinate plane here. And we'll draw a simple quadratic curve. We'll make this one going up. Now the axis of symmetry is what the curve is symmetric about. So quadratics have symmetric end behavior. Either both sides go up or both sides go down, but it's also a mirror reflection. The left of a quadratic curve is identical to the right of a quadratic curve. The only difference is that to the left and to the right they look different, but the distance from that axis of symmetry is the same. Where that axis of symmetry hits the curve, we call that a vertex. All right? And this right here, this dotted line, is the axis of symmetry. Now, in order to find the axis of symmetry, there's actually a pretty nice formula. That formula is x equals negative b over 2a. So if you look at that definition of a quadratic function, ax squared plus bx plus c, whatever b is, the middle coefficient, you take the opposite of that, make it negative b. So a positive becomes a negative becomes a positive. That gets divided by 2a, 2 times your leading coefficient. And this axis of symmetry actually feeds into the vertex. Now the vertex is an ordered pair. So your vertex has coordinates x, comma, y. Well, the axis of symmetry hits the quadratic curve at the vertex. So that means that the x-coordinate of the vertex is also the x-coordinate from the axis of symmetry. So our vertex has an x-coordinate of negative b over 2a. Now to get the y-coordinate, the x and y coordinate of the vertex are related to each other. Whatever you plug in for x, you get for y. Well, the x value you plug into the function itself to get your y value. So your y value will be f of negative b over 2a. So whatever your axis of symmetry is, that is the x-coordinate of the vertex. Go ahead and plug that into the function f, and that'll give you your y value. So to kind of see this in action, all right, find the axis of symmetry and the vertex of the following quadratic functions. So we have this negative 3, that's going to be our a value. We have 12, which is b. We have negative 7, which is c. So to find your axis of symmetry, our formula, negative b over 2a, so negative of the b value, so negative 12, over 2 times your a value, which would be negative 3. So that gives us negative 12 over negative 6, which is 2. So our axis of symmetry is x equals 2. Now that is where the axis of symmetry intercepts our quadratic curve. The x-coordinate there gives us the y-coordinate if we plug it into our equation. So, to get our vertex is 2, comma, f of 2. So f of 2, take 2, plug it in for x in our original function, and if you do that math, you should get 2, comma, 5. So we have our axis of symmetry, and we have our vertex. You use that formula, negative b over 2a, to get your axis of symmetry. That answer is also the x-coordinate of your vertex. Plug that answer into the function to get the y-coordinate of your vertex. This example you can take a look at, check with the completed notes on my website. The other thing I want to introduce about quadratics is different ways that you can write a quadratic equation. So, if you remember back to section 1.3, it was all about equations of lines. There's a ton of different forms for equations of lines. Well, we have a couple of different forms for quadratic functions as well. We have our general form, which is the definition, which you already saw. F of x equals ax squared plus bx plus c. And that c value is a constant. However, it also serves another role. If you plug 0 in for all of your x's, your ax squared, your bx cancel out, all you're left with is c. Well, think to yourself, what points on a graph all have an x-coordinate of 0? What points on a graph all have x-coordinates of 0? That would be any point on the y-axis. So this constant is also your y-intercept. Now we also have standard or vertex form. So f of x equals a, x minus h squared, plus k. Now the h and k values, h can be an x-coordinate, k can be a y-coordinate, and they end up being the x and y coordinates of the vertex. So that's why we call it vertex form, okay? This is the x, and this is the y. H is the x, k is the y of your vertex. So kind of like slope-intercept form tells you the slope and the y-intercept, vertex form tells you the x and y coordinates of the vertex. So looking down here at these two problems, okay, here's one that's in standard or general form, and here's one that is in standard or vertex form. Now, I want you to sketch a graph of each quadratic equation provided, also find the zeros or the x-intercepts. So depending on the equation they give you, you kind of start in a different spot. So for r of x, this is general form. So we know the y-intercept, okay? We can pretty easily find the axis of symmetry, negative b over 2a. You could find the zeros either by factoring down, so, you know, 2 sets of parentheses, or, you know, something that always works is the quadratic formula. So you have some options as to what you can do to graph that equation. Based on the form they gave you, here's a starting point to do that. For standard or vertex form, now this automatically gives you the vertex, the values h and k. The h value, the x-coordinate of the vertex, is also your axis of symmetry. To find your zeros, just take your function f of x, make that 0, and then you can solve. So subtract 2 over, divide by -2, square root, and all that. So depending on the form they give you, you can create a graph of both of these, but you might start the problem in slightly different ways. So you can get graphs of these, identify the zeros, x-intercepts, and then check the answers to my completed notes online.